we've covered solving triple integrals with cylindrical coordinates, but we need to cover an additional coordinate system, the spherical coordinate system. So if you go back and remember how we describe the spherical coordinate system, the basic idea is you can think of a sphere. And when you think of a sphere, you think of it having a radius, and any point on the sphere can always be determined by having that radius to that point, and its internal determination is simply how your in thinking a lot of in flight terms, you think of things in terms of azimuth and elevation, right? That's the idea. In spherical coordinates, it's a little different. You have what you might think of as an azimuth, where you're changing your theta that you're rotating on, but you have, instead of an elevation going from the ground up, what you have is some sort of meridian, and you're falling off from that z-axis. You're falling down to the point. So if I could think of this is a coordinate system here, where what I have is I have my positive z-axis, and I have, if I'm going to this point, this rho, which I always draw a lot like a P. I'm trying not to, but it just happens. You have a rho, which is the distance to the point. And once you have the distance to the point, you can determine the angle it makes sort of winding around the z-axis, and the angle it makes falling off of the z-axis onto the point. That's the way I always think about it, is if I were to have a plank of wood on that point, and something off the z-axis just fell and smacked it, what would that how far would that rotate? What's the angular change there? And so you have this phi, you have this theta, and so you have rho, phi, and theta as your coordinates. So instead of x, y, z, or instead of r theta z, you have rho, phi, theta. And so you have these properties. In this particular case, rho is never negative because it's the distance to a point. So it could be 0, but it's usually positive. Phi goes from 0 to pi, because what that happens is that fall off angle where you say, all right, I start and I can only fall down and smack the bottom. I can only smack the bottom, the negative z-axis. So I can't do a full rotation. I can just fall and smack it. And then theta is what twists me around. So you might say, well, what if I need to fall backwards? Well, you don't need to fall backwards. What you do is, instead of falling forwards, you rotate with theta, and then you fall forwards. So again, instead of falling backwards, you rotate and you fall forwards. So theta needs to be able to spin all the way around. So it spins everything, and then just, again, it falls off from there. That's kind of how I envision it. And there's these special relationships. Again, rho squared is x squared plus y squared plus z squared. So usually think of rho as the square root, right? That's the distance. And you have these special relationships: rho sine phi cosine theta, and rho sine phi sine theta. Now, what's probably easier to think about is that r is rho sine phi. So if you look at phi here, if I were to draw a sort of a dotted line making a right triangle here, sorry, not right triangle there, right triangle here, then this is the same as r. That's the same as r. It may not look like it for perspective. That's just because I did a bad job drawing. But the idea is sine of phi, rho sine phi, or no, I was right the first time. It's got to be like here, because this is your hypotenuse. Anyway, my apologies. But rho sine phi is r, and if x and y are r cosine theta, r sine theta, like they are in cylindrical coordinates, to me that's the easier way to keep up with it. I know I can usually think through cylindrical coordinates, but I have a hard time thinking about spherical in terms of these formulas, so I remember this, and then I just plug that in here. Now z is rho cosine phi, and that's not too hard to remember because rho squared is r squared plus z squared, and this is like a sine squared plus cosine squared identity thing. Just however you need to keep up with it. Anyway, you can use these to convert your equations. Something I didn't write, something I definitely should have written, and now I'm going to, is that, for on Q, if theta 1, so if theta is bounded by some constants, phi can be written as a function of theta alone. And basically what you do is you say, all right, well, if you can write rho as a function of x and y, then what you really are doing is writing a function of this nasty I need to copy that. But the idea is if you can describe these with this here, what we can do is we can generate an iterated integral. We can say that then we can say this, we can essentially do the same thing we do with cylindrical coordinates or rectangular coordinates and say that the volume can be written as some sort of iterated integral as long as you can always describe one of these in terms of constants, and you can describe each subsequent one in terms of the previous variables alone. So if you can do that, then you can construct an iterated integral instead of a standard triple integral. And that's really what we're trying to do here, because iterated integrals are really, without being extra fancy, are really the only way you're going to be able to find these values. So we'll do an explicit function and try to merge all this information so we can go forward.